Describe the rate of change of the blue curve at the red point in the direction of the red arrow. Hello, welcome back to the Quant Plus YouTube channel. Before we begin today's video, I wanted to thank those of you who are supporting the channel. I am continuing to see growth. I'm starting to see more interactions like comments. I see more likes, more views, and the video yesterday about proof by induction seems to be doing rather well. So I just want to take a moment to thank those of you who are continuing to support this channel. Jumping to the concept for today's video, the key concept that will allow us to solve the problem posed at the introduction to this video is that of the directional derivative. So the directional derivative generalizes the idea of partial derivatives along the coordinate axes and the gradient, and allows us to consider the rate of change in arbitrary directions. So you may be familiar with concepts such as df dx representing the partial derivative of some function f along the x axis, or the x in the x coordinate, or df dy, the partial derivative of the function f in the y direction. And so the directional derivative takes it a step farther and allows us to, for example, describe the rate of change of the function along the direction described by the vector 1, 1. And the more formal definition of the directional derivative is that the derivative in the direction of v of some function f of x is defined as the limit as h approaches 0 of f of x plus h times our vector v minus f of x over h, where again f of x is defined as some multivariate function, let's just say a function of the variables x1 to xn, and our vector v is a vector with n components, v1 to vn. Now, while this is the formal definition of things, this definition is rather annoying to work with because it involves a lot of algebraic steps, and it can be potentially error prone. So a much more user-friendly formula for determining this would be del f of x dot v, where del f, or the gradient of our function f, is defined as the vector of partial derivatives. So starting with our partial derivative with respect to x1 in our first coordinate, all the way up to our partial derivative with respect to xn in our nth coordinate. And tying it maybe to 3 dimensions where a lot of people are a little bit more familiar, we can think about it as our x, y, and z axis, where our first component of our gradient is our partial derivative of our function with respect to x, our second is our partial derivative with respect to y, and finally our partial derivative with respect to our z coordinate. And v is some vector where if we're dealing with 3 dimensions, this vector would have 3 components, let's just say 1, 1, 1. So jumping back to the example at the introduction or the opening of this video, let's consider that the blue curve is defined by the equation z equals x squared plus y squared. The point that we're interested in the behavior, or the point at which we're interested in the behavior of the curve is the point negative 1, 1, 1. And the direction that we care about, our vector v, is negative 1, 3, 1. So the first step I'm going to take here to make it make a little bit more sense is to rewrite our first equation, z equals x squared plus y squared, in terms of f of x, y, z is equal to x squared plus y squared minus z equals 0. Because in doing it in this way, first of all, this is an equivalent expression of the same idea, but it also makes more sense to describe the gradient in this way, because the gradient of this function f would have three components matching the three dimensions that we're working with here. The first step I'm going to take is finding the gradient of our function f. Our partial derivative of our function f with respect to x is 2x. Partial with respect to y is 2y. And finally, partial with respect to z is -1. Evaluating our gradient function at the point of interest, -1, 1, 1, we get the vector -2, 2, -1. And then considering our our directional derivative formula, then we're going to consider the dot product of our gradient evaluated at our point of interest and our vector v. So our gradient at this particular point is -2, 2, -1, and our vector v is -1, 3, 1. The dot product of these two vectors is going to be 2 plus 6 minus 1, and that's going to be 7. And intuitively, this result makes sense, because we can see visually that the direction of the red arrow is in the same direction that the function value is growing. At least if we consider it in terms of z equals x squared plus y squared, it's clear that the red arrow is pointing in the direction where z is becoming more positive. So that result kind of intuitively makes sense. To summarize the concept from today's video, a directional derivative is pretty much a generalization of the idea of partial derivatives, and it lets us consider the rate of change in some kind of arbitrary direction. We calculate this directional derivative by considering our gradient and finding the dot product of our gradient with the vector that describes the direction of interest. If you found this content informative, please continue to support this channel. You can do that by liking this video, subscribing to the channel, sharing this video with your friends and family, or even leaving a comment. I really appreciate the feedback. If you're interested in one-on-one tutoring sessions, please follow the link in the description below. Have a great day.